Okay, today we're going to talk about functional groups. We've been talking about organic molecules and hydrocarbons, and now we're going to put groups of atoms on the structures, on these hydrocarbons. And these groups of atoms, which are called heteroatoms, these heteroatoms, which are usually not carbon and hydrogen, although they can contain carbon and hydrogen, but they're not just hydrocarbons like we've been seeing before. These are heteroatoms, as opposed to homo. Homo, the prefix means the same, hetero means different. So these would be groups of atoms with something more than just a carbon and a hydrogen in them. Some of them contain both, but in various different configurations. So we're going to talk about functional groups. And like the name implies, it's a group of atoms. So functional groups here. Here's our definition. It's a group of atoms attached to an organic molecule and remember, organic compounds are anything with carbon in them, except for the exceptions that we talked about, of course. And these groups of atoms that are attached to an organic molecule that also give it its function, hence functional groups. Okay, so my characteristic there kind of went down the side of the page, but that's what we're looking at. So these are our functional groups. And in your book talks about 9 different functional groups. I want you to know 5. The first of which are alcohols. Alcohols are formed when you have an oxygen and a hydrogen attached to some structure. So whatever that structure is, doesn't matter. That oxygen and hydrogen are on there. That makes it an alcohol. And sometimes you'll see this written as just an OH next to each other, like that. And what this means is that the oxygen is bonded to both the hydrogen and to the hydrocarbon, or whatever the larger molecule is over here. So that's what we're looking at here. And this OH group is called an alcohol group, but it's also called a hydroxyl group. Hydroxyl. And again, that refers to the fact the hyd part refers to the hydrogen, the oxy part refers to the oxygen. Okay, so the nice thing about organic molecules is they tend to have nice patterns with the naming, so that's what we're seeing here. Okay, so here's our alcohol. Our simplest alcohol then is going to be 1 carbon with an alcohol group on it. And if I draw out my Lewis dot structure for that, it would look like this. Okay, and again, I'm drawing the oxygen and the hydrogen together, but it would really look like this, where the oxygen is bonded to the hydrogen. That's what's implied by putting them together. It's kind of like our condensed formulas. All right, because we have 1 carbon, then the prefix meth is used. Everything is singly bonded, so if this was a hydrogen instead of an alcohol group, it would be methane. So let's go methan. And then the ending alcohol, OL, is going to give us our ending on this guy. So this is called methanol. I don't want you to spend a lot of time knowing the naming patterns for these, but I do want you to recognize the first 3 simplest alcohols, and the first is methanol. Methanol, with my 1 carbon here, is also called wood alcohol. And the reason for that is because it's made from distilling wood. You can get alcohol from distilling a number of different types of organic materials. Again, organic meaning that it contains carbon. And when you distill wood, then you make methanol. And back during Prohibition, so Prohibition when they had outlawed alcohol, some people would resort to distilling down their furniture or even sawdust anything that they could distill to get alcohol out of it. And when they were distilling wood, were making methanol, and methanol is incredibly dangerous to human beings, at least for drinking, but it's a really good solvent. And like our solutions chapter, we talked about things that dissolve other things well. It's a good solvent. Part of the reason for that is this alcohol group. This alcohol group can do hydrogen bonding when we were talking about intermolecular forces, so it dissolves things pretty well. And it's also used as an octane booster in your gasoline. And while it's doing this octane boosting, it also acts as an anti-icing agent. So that means that it prevents your gasoline from freezing. So that's kind of a useful thing as well. That's methanol. Again, our pattern here is that the prefix tells you the number of carbons, the ending tells you something about the characteristics of our organic molecules. Alright, so that's our first alcohol. The second alcohol has 2 carbons in it. So if you see 2 carbons, you should already be thinking eth, and you would be correct. So here's our 2 carbons. If I put an OH group off, and I'm going to do this as the structural formula, so I'm showing my bonding, except on my functional group. Then the 2 carbons means that my prefix is eth. It's ethane because it's all individual carbons, single bonds to my carbons, and then it's got an alcohol group, ethanol. Ethanol is the alcohol that's present in spirits. It's in beer and wine, and it's drinkable alcohol, if you want to think about it that way. And when I say drinkable alcohol, I of course mean for responsible adults over 21, which then is of course a joke, but this is more safe for us to drink than methanol is. Ethanol, of course, is produced during fermentation. It's a byproduct of fermentation, which is when yeast is reacting with sugars. So yeast is eating, if you want to think about it that way, the sugar and producing carbon dioxide and alcohol. So that's the fermentation process. And we usually will measure the concentration of alcohol or of ethanol in proof. So if you've ever heard the proof of the liquor, this also is a prohibition term. It came about because people wanted to show how much alcohol was actually present in their drinks, so they had to prove it. So the proof became the way that they measure concentration. And remember, concentration is the amount of solute per solvent. So in this case, we're talking about the amount of alcohol per solution, which in this case is going to be some mixture of alcohol and water. And proof is equal to 2 times the percentage of alcohol in the solution, or in the beverage, if you want to think about it that way. So if you have something that's 100 proof, if you've ever heard of this term in terms of liquor or distilling or anything like that, if you have something that's 100 proof, it means that it's 50% alcohol. Okay, which is 100 proof is crazy high. And so 50% alcohol is really, really strong. It's very concentrated. Most of it is more watered down than that, for good reason. Another use for ethanol. Ethanol is another gas additive. And you'll see again, like, 10% ethanol added on your gas pump. You know, whatever percentage it is. Usually about 10. So that is used as an additive in gasoline for similar reasons as methanol. Again, it kind of helps to boost your octane, and it helps things to burn just a little bit cleaner. You don't need a lot of it to do that, and it also acts, especially in the winter time, as an anti-icing agent. This is also used as an industrial solvent. It dissolves things really well. Okay. Alright, so that's a little bit more on ethanol. If we increase our number of carbons, if we have 3 carbons, for instance, then now our prefix is what? Are you already thinking about it? Hopefully. I'm going to put my alcohol group on the middle here. I could put it on the end. If I put it on the end, it would be called propanol because of my 3 carbons. When I put it in the middle like this, it's called isopropyl alcohol. So the prop here refers to the fact that there's 3 carbons. Iso means that it's an isomer of propanol. And this is a structural isomer now, so instead of having an alcohol group on the end, either one, I put it on the middle here, so I made it different, right? So same chemical formula, different bonding pattern, different configuration means that it's an isomer. So isopropyl, 3 carbons, alcohol. Now you should recognize isopropyl alcohol. This is rubbing alcohol. Which you find in your bathrooms, and the reason that rubbing alcohol is used in our bathrooms or in the hospital is because it's a disinfectant. And that's true of all of the alcohols as well. So sometimes you'll see those old westerns or something where they have a bottle of whiskey and they pop off the top of the bottle of whiskey and pour it onto their cut or their gunshot wound or whatever. So part of the reason for that is to disinfect the wound. And that's why it works. So alcohols in general, if we're talking about characteristics, and again, we care about kind of what the characteristics are because when we add a hydroxyl group to a hydrocarbon, that's going to give it these characteristics. So some of these characteristics are the fact that it's a disinfectant, or an antibacterial type thing. It kind of helps to clean things out. If we have more concentrated alcohol, it can be used to industrially clean things. So again, that's part of its functionality. It's a good solvent. It dissolves things well. And the last characteristic is that it's really volatile. Volatile, that's, I think, a new vocabulary word for us. So volatile means that it evaporates quickly. And you can see that at home with your isopropyl alcohol. If you pour a little bit on the counter, for instance, as you're wiping something out or cleaning something off, then it evaporates really quickly. So it's volatile, and that allows for some different chemical reactions and chemical processes and chemical characteristics to occur, which kind of go beyond the scope of things. But those are some characteristics of alcohol. Now, building on that, here's the second functional group I want you to know. I want you to know phenols. If we look at the ending here, the OL ending indicates that I'm probably going to have something that's akin to an alcohol. Okay, again, there's consistency in the naming for organic molecules, and phenol is a benzene ring with an alcohol group on it. So we have a benzene ring with a hydroxyl group on it. And I'm going to come back to this because we haven't talked about benzene, although you guys played around with it in the modeling activity today. So let me do a little bit of an aside on benzene, and then we'll come back to phenol. We have talked about benzene before when we talked about toxic waste. Benzene is a carcinogen, which we said means that it causes cancer. It's used as an industrial solvent. And we'd use it in a different way than we use alcohols because benzene is all non-polar. Okay, so it's a non-polar molecule. The chemical formula for benzene is C6H6. And benzene was known for a long time, so people knew what the structure, or they knew what the chemical formula was for benzene, but they didn't necessarily know what it looked like. So for a long time they knew that C6H6 was benzene, and this was actually discovered by a man named Michael Faraday. Michael Faraday did a lot on electricity and such, so Faraday cages, the reason that planes don't get struck by lightning when you're up in the sky during an electrical storm, or why when they do get struck by lightning that you don't get hurt, is because of Michael Faraday. So he was the one who discovered it, but they could never figure out if it was what the overall structure was, because that means that we have a 1-to-1 ratio of carbons to hydrogens, which is kind of bizarre. And so it was Friedrich August Kekule that figured out structure. And the story goes that it came to him in a dream. And we've heard of a lot of chemists that things came to them in dreams, and take that with a grain of salt. But he said that he had a dream about a snake eating its own tail. And he said, well, aha, the structure of benzene must be a ring, which I think, going from snake eating your own tail to ring structure for benzene is a little bit of a stretch, but there you go. So what he found is that these carbons will form a ring. There's 6 of them in a ring, and I have enough hydrogens for one hydrogen to come off of each carbon. And that's all I have to work with. So if I look at my hydrogens are happy because they each have 1 bond. But my carbons only have 3 each. So what he figured out is that every other bond had to be a double bond. So every other bond had to be a double bond, which means that these carbons then are unsaturated, right? We said anything with double bonds in it are unsaturated, because carbon wants to make 4 bonds, or it wants to be attached to 4 things, but it's only attached to 3. Okay, so we have an unsaturated ring here. And we have the ring that's done this way, and if I put it in my lightning bolt diagram, or in a backbone diagram, then this would look like this, which is kind of a nice way to do it. And it's just as easy, or just as likely, that it would look like this, with every other one going this way, right? So it could be either or. And in reality, it's actually a little bit of both. So when we are symbolically showing benzene, and you may have already run into this in your reading and research, then a benzene ring is usually represented like this. And the circle in the middle indicates that there's these alternating double bonds here. Okay, so 1, 2, 3, 4, 5, 6 carbons with alternating double bonds. That's benzene. Okay, anything that has benzene in it is called an aromatic compound. Aromatic. And the reason that they originally named compounds with benzene as aromatic is because this comes from the word aroma, right? And aroma means smells of some sort or scents. And so they found that a lot of things that contained benzene had smells, for good or for bad. Now it turned out that this wasn't always the case, but the name stuck. So anything that has a benzene in it is an aromatic compound. So for example, there's one compound that looks like this. So I'm going to draw a benzene ring. And then I have another benzene ring attached to it. Okay, and then here's my double bonds in this one. Here's my double bonds in this one. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons, and then as many hydrogens as will fit around for each of these things. And this compound is called naphthalene. It is also not very good for you, naphthalene, but it's a good illustration of a smelly compound because naphthalene is the molecule that's responsible for the smell of mothballs. Which, if you've ever smelled mothballs, then you know are quite fragrant and quite terrible smelling. Okay. Another compound that has benzene in it is this guy. And again, I'm going to draw this with a lightning bolt diagram. And we'll get used to looking at these in a second. I'm going to give you guys a worksheet to look at, to where you have some practice looking at larger molecules using these backbone diagrams, because we get into compounds that are quite large with lots of different stuff in them. Okay, so here's my benzene ring. I have an alcohol group off of it. This whole group, and this is kind of what we're building off of here, this whole group is a phenol group, which we'll come back to. And then this is a carbon with a double bond to an oxygen. This is a carbon, oxygen, carbon here. So this is actually called an ester, which isn't something that we're going to get into, but you know, just to kind of let you know, look at it. The name of this molecule is methyl salicylate. Methyl salicylate, and it is responsible for the smell of wintergreen. So if you like wintergreen mint kind of gum, then the reason for the smell is this particular molecule. Okay, and some other characteristics of it, but for now that's kind of what it is. So that's why we say that these compounds are aromatic, because many of them that do contain benzene rings, like these examples here, do have a nice or bad smell to them, one way or the other. Okay, so that's aromatic. Let's get back to phenols then, because that's where we started all of this. So the simplest of the phenols is just a phenol molecule, which is now our benzene ring with an OH. This is just called phenol. As we saw with our methyl salicylate, this could be part of a larger molecule, and it is still a functional group. It will give function to the structure, but this is our simplest of the phenols. And phenol is used as an antiseptic. Okay, so phenol was really important in surgeries back in the day. So, you know, modern medicine has really developed out of a lot of different eras and a lot of different time periods. And one of the major things that has changed the way that we view medicine is germ theory, right? Once we figured out that there's little things that exist on the surfaces of other things that can cause problems for us, then we figured out that cleanliness is more important. And so one of the things that they used to use was phenol to clean surgical instruments like the scalpels and such. But what they found is that phenol is very harsh on human tissue. And by harsh, I mean that it's just kind of abrasive. It's it makes it painful. It's not very pleasant, and it's not very good for the tissue itself. So if you have really concentrated phenol, then this was really something that caused more damage than good when it came to these surgeries. So yes, it kept things clean, but it didn't really help with the patient's overall happiness. So what they found is that there's this property, but it can be diluted, and we can use these dilute solutions of phenol and help rinse out different orifices. So dilute solutions of phenol are used for things like mouthwash. And the scientist that first discovered this was a man named Joseph, wait for it, Lister. And so Listerine came from Joseph Lister and these dilute solutions of phenol. Okay, it's also used in throat lozenges. So if you go home and you have some mouthwash or chloroseptic sprays or throat lozenges, cough drops, those will all have phenol as an active ingredient. And it was Joseph Lister that first figured out those antiseptic properties. Okay, so there's 3 more that I want to talk about. The first are ethers. And ether is also related to surgeries and medicine because ether was originally used as an anesthetic. So anesthetics in surgery are used to knock you out. They used to use things like chloroform, which they found actually killed more people than not, so they were trying to find something else. And ether is very volatile, which in the case of ether, when you're trying to use it for something like a surgery, if you breathe it in, it means that it gets into your bloodstream quickly. And will knock you out, but then at the same time it will also get out quickly, so it won't keep you under for very long and it won't cause it to build up and kill you, essentially. So it gets into and I guess out of the bloodstream quickly, which is a positive thing. That was a positive step in the right direction. So an ether I like to call a carbon-oxygen-carbon sandwich, and it looks like this. So these carbons can be connected to anything else, right? And the oxygen is in the middle. The oxygen is going to be bent because it's got these 2 lone pairs on it, and it's not going to want to bond to anything else. So it's basically a carbon-oxygen-carbon sandwich. And the simplest then would be if all of these are hydrogens. So it would look like this. I'm going to do the condensed formula. And this is called dimethyl ether. Dimethyl, di meaning 2, these are both methyls, and then the oxygen's in the middle. It was actually diethyl ether that was used in surgery, so that looks like this. Okay, so diethyl ether, there's that at the bottom. So a carbon-oxygen-carbon sandwich is something that you'd recognize as an ether. One of the favorite chemistry jokes and chemistry puns is if you have a structure that looks like this, okay, then that would be a carbon-carbon here, there'd be a carbon-carbon here, and it kind of looks like a rabbit this way with the ears on it. And so this would be an ether bunny. Yeah, you can groan. So just so that you can see it in a structure here, this is your carbon-oxygen-carbon sandwich, and that's the way that that would look. Okay, so actually not what it's called. This is actually this backbone structure to what we just saw, the diethyl ether here. Okay. So here's my 2 carbons, that's these guys. Here's my 2 carbons, that's these guys. So it's diethyl ether. But they like to be funny and punny, especially in organic chemistry. There you go. So there's your ether. The last 2 groups are aldehydes and ketones. So let's start with aldehydes. Aldehydes and ketones both have one major feature in common, and that's a carbonyl group. And a carbonyl group looks like this. It's a carbon double bonded to an oxygen that's attached to something and something else. Okay, so this is a carbonyl. That's just that feature of this functional group. And an aldehyde is going to just have a hydrogen here. So an aldehyde is always at the end of a molecule. So it's always going to be that last hydrogen there. So you might have a structure that looks like this. Here's my double bonded oxygen, here's my hydrogen. And this would be an aldehyde group right here. Again, we'll do some practice with these types of molecules. Now, aldehydes in general are smelly also, so they get kind of stinky. And the simplest of the aldehydes is if this thing that it's connected to is just another hydrogen. So the simplest of the aldehydes looks like this. And its common name is formaldehyde, which you probably recognize. So it's got the word aldehyde in it, so you know it's going to be an aldehyde group. Form actually is another way of talking about one carbon. So formaldehyde is the simplest of the aldehydes, and it's used to preserve decaying and dead tissue. So if you've ever taken a biology class where you had to do dissections and then you kind of smelled the stuff coming off of the things that you were trying to dissect, it's generally unpleasant, and that would be the formaldehyde. It's useful though because it is preserving the tissues. So that's 4. And then 5 is the ketone, and ketone also has a carbonyl in it. Ketone. And it looks like this. At its simplest, it's got a carbonyl with a carbon on each side. So here's my carbonyl group in the middle. There's a carbon on each side, and these carbons can attach to anything that they want. So if you were looking at this in a structure, it wouldn't be at the end, it would be in the middle. So it would look something like this. So here's this. This would be the ketone group right here. Okay. At the most simple, the simplest ketone would be if all of these guys are hydrogens. So I'm going to do the condensed formula again. Here's my H3. Here's my carbon. And here's this guy. Okay, so carbonyl with a methyl on each side. And this is called acetone. So the simplest of the ketones has 3 carbons, right? So because it's in the middle, it's sandwiched between 2 other carbons, this is the smallest structure that can occur and still be a ketone. And so this is acetone, and you've probably heard of acetone before. You'd at least recognize the smell. It's the primary component in nail polish remover. Okay, so it smells like a salon, basically, and it's used as a solvent. It dissolves things really well, which is why it takes off nail polish so well. Okay, so that's our ketone. So we have basically 5 groups that I want you to know. Alcohols, which have the hydroxyl group, the OH, and phenols, which also have the OH. Ketones and aldehydes, which both have these carbonyl groups, and then ethers, which are the carbon-oxygen-carbon sandwiches. Okay, so these are our 5 functional groups, and if you have any questions on these, please don't hesitate to let me know, and we'll talk about it more in class next.